So IARPC is the Interagency Arctic Research Policy Committee. It brings together leaders from 18 agencies across the U.S. federal government. IARPC includes IARPC Collaborations. IARPC Collaborations is a platform that connects federal government researchers as well as non-federal researchers, including academics like myself. It also connects us with Arctic communities. About the Coastal Resilience Community of Practice. So this community of practice is, of course, a community of researchers and practitioners working to enhance Arctic coastal resilience. The co-leads include myself. So I'm Tom Ravens. I'm an Arctic coastal engineer at the University of Alaska, Anchorage. Christina Bonzel, who's just waved, is a marine ecologist at the Bureau of Ocean Energy Management. Tazai Jones, also a co-lead, is the Coastal Steering Co-Chair at the U.S. Fish and Wildlife Service. And our fourth co-lead is Elizabeth Walsh. She's a research fellow at the Scott Polar Research Institute at the University of Cambridge. So this meeting is a follow-up to a meeting that we had about a year ago when we attempted to address some of the deliverables in the IARPC implementation plan for the 2022-2026 Arctic Research Plan. And this particular meeting is going to focus particularly on deliverable 2.3.7 of the implementation plan, which is to improve high-resolution models' ability to capture coastal processes at the interface of ocean, land, and atmosphere by supporting targeted collaborations among model developers, users, and decision makers. So I think that fits us pretty well. We have Lee Erikson is going to lead us off, and then Martin. I think everyone knows Lee Erikson from the USGS. Martin Henke is a recently minted PhD student from George Mason University. So Lee, you're on. Thank you.
So it's actually going to be me who's starting, Tom. Okay. So I'll start off. The narrative is that I'll be starting at a regional scale, and Lee will be following up with the local analysis. So without further ado, I'll get into my presentation. So as Tom mentioned, my name is Martin Henke. I'm a PhD candidate at George Mason University, but I, as he alluded to, recently defended my dissertation. I'll be graduating here in 3 weeks. I'm at George Mason University, specifically the Flood Hazards Research Lab, headed by Dr. Celso Ferreira. And that's located in sunny Virginia, which is much warmer than Alaska right now, but I am originally from Anchorage, Alaska. And so I'm very happy to be presenting some of the research that I've undertaken in the course of my degree that's relevant to our state. It's titled Investigating Future Coastal and Marine Wave Hazards in the Changing Arctic. I look at the Arctic as a broader, most of my simulations look at the Arctic as a whole, but the analyses typically focus on areas more relevant to Alaska. So I should also acknowledge that the source of my funding comes from the NSF NNA grant, Arctic Impacts and Reverberations of Expanding Global Maritime Trade Routes. And without further delay, I'll get into the content of my presentation. So with growing Arctic wave hazards, I suppose I'm presenting to the coastal group, so I don't really need to spend a lot of time explaining that there's been significant growth in wave hazards experienced along most North American Arctic coastlines. And this is evidenced through the satellite record, reanalysis, and even observation for many communities. And in the absence of being able to build protective infrastructure, many communities are being threatened and forced to retreat from coastlines and that growing hazards. It's important to also, within the context of Arctic wave hazards, acknowledge that there's a unique dimension for waves and how they threaten the coastline or maritime activities. For example, waves in the coastal zone can exacerbate permafrost thaw and lead to slump and further erosion in that coastal zone. But then also within the marine environment, sea spray generated from interaction between large waves and ships or coastal superstructures can lead to ice accretion on the actual ship and lead to slowing of the vessel, disabling it, or even capsizing the vessel. Before moving forward, I'd also like to mention that with that increase in the magnitude of hazards, wave hazards, there's also increasing exposure due to interest in regional development through maritime shipping, tourism, or resource extraction in the Arctic. So really that risk is compounding with increasing exposure and the rise in the magnitude of hazards. So what do we actually know about projecting future waves? The current academic literature shows that with increasing open water area, there are going to be significant increases in the Arctic wave climate. And as we progress towards the projected ice-free Arctic, which is projected to occur in the coming decades, there's sizable increases in the wave hazards. I'm borrowing a figure here shown on the right from a recent publication from Casas-Prat entitled Wind Wave Climate Changes and Their Impacts, recently published. And you can here see the percent change in the mean significant wave height at the end of the current century relative to the historical epoch. If we're looking at the historical, at the central Arctic rather, you can see that 400% increases in the mean significant wave height are projected by that end of the century. But even along Alaskan coastlines, we're seeing 100% increases. So really a doubling of the mean significant wave height, which is substantial. However, there's some real significant gaps in the state of our knowledge of future Arctic wave hazards, and that's surprising given the severity of the predicted change and the fact that it's already having significant impact on coastlines. One is that there's a lack of assessments to assess uncertainty. Climate models themselves are best tool for predicting the future climate and environmental change. They don't actually simulate waves. And so it requires an independent effort to go in or independent effort and employment to go in and simulate future waves. Beyond that, many global wave projections that currently exist are really only global in terms of name, because they're not simulating wave hazards at high latitudes due to computational restrictions in the model. Beyond that, much of the existing literature is becoming out of date as it uses the previous generation of climate models as independent foreseens. That would be CMIP-5, the Climate Model Intercomparison Project's 5th phase. And this has noted limitations in representing storm climatology, which of course could affect our estimations of storm waves and the associated hazard levels. And then finally, there's very few high-resolution regional or coastal analyses. Most of the existing literature is really looking at this large pan-Arctic scale. With the exception of a few other researchers, most of the existing literature really doesn't look at, say, the wave hazard season occurring in the mid-fall to late winter or early winter, or looking at a coastal scale. So really, from these gaps in the literature through my research entitled Project, the overall goal of my research was to project and assess future Alaskan Arctic coastal and marine wave hazards. Here, we employ the latest developments towards wave modeling in Arctic environments, critically wave ice parameterizations, how the wave model actually simulates the interaction between waves and the sea ice, and how the sea ice attenuates and scatters wave energy. Also using updated high-resolution climate model forcings, either coming from the Climate Model Intercomparison Project's sixth phase, or models that have less than a quarter degree of resolution, so that they can resolve tropical storms or Arctic cyclones at high altitude or high latitudes. And then finally, analyzing at scales and seasonal windows applicable to regional stakeholders. So looking at the season, looking at the fall season or at coastal zones, so that these projections or of the wave hazards are more applicable to people within the region. And so given these goals and the primary objective. I'll go ahead and get into a recent study that was published coming from our laboratory, and it's titled Increasing Coastal Exposure to Extreme Wave Events in the Alaskan Arctic as the Open Water Season Expands. It was published in the journal Nature Communications, Earth and Environment. And the objective was to evaluate how Arctic coastal wave hazards resulting from a storm event are augmented under future sea ice conditions, and then to establish a window of seasonal exposure. The methodology that was employed in this study is quite simple. So we have a historical storm with its associated meteorology and its sea ice, and that's fed into ADSRC-SWAM, which is a water level and wave model. So we can simulate coastal water levels and the waves that are impacting due to the storm. And we get essentially a wave simulation that corresponds to that historical event. We then repeat the simulation, taking a climate model ensemble, 14 climate models here, and we repeat that simulation, replacing the historical sea ice with ensemble sea ice projections. So that's producing many future wave simulations, and we're averaging over those to finally get comparison metrics. So we're assuming the meteorology doesn't change and that the sea ice is being substituted with that future projected sea ice. So first step is to discuss the storm that was simulated. It was the 2016, December 2016 storm, which impacted the Chukchi and Bering coast. Here you can see it coming, well, let's let it restart. In the figure to the right, you can see there's the pressure front coming up, passing through the Bering Sea. It obviously was a quite intense storm with a low central pressure. Very high wind speeds that impacted coastal areas and caused significant damage for many communities. It caused a large storm tide for much of the Chukchi coast and certain areas around the Bering Sea. However, notably, as you can see in the figure to the left, we've got the actual sea ice that was present during the time of that storm. You can see that there's sea ice all along the northern coast and much of the western coast, protecting those coastlines. And this was actually commented on in several of the publications that I read leading up to this study, that the sea ice present during the storm protected several communities from wave effects. So it made an ideal storm to really simulate and look into. Getting into the wave simulation here, we can see significant wave height, simulated significant wave height, and this is the average of the highest 1/3 of waves. And you can see that the storm is generating waves exceeding 8 meters in certain locations. So these are some really large waves propagating through the Bering Sea. I should mention here that most of these, that this event's wave simulation was validated in comparison to satellite data products, just to make sure we're accurately simulating the associated wave hazards. But if we're looking at this historical event, you'll notice that the sea ice contours denoted by those thin white lines, really all those waves are being dissipated as they approach the Bering Strait, and you can actually kind of observe waves press the ice further up north. But then even along the Bering coastline, we're not seeing much very high waves reach that area because of the presence of sea ice. Now looking at a future sea ice field, this is for the high emission scenario in the 2070 realization for the climate model people, the SSP 585 scenario. And this is important to mention, this is just a single realization. As I said, we're producing many future simulations for each scenario and the associated year. And you can see this is an entirely different story. We can observe that many of these swells are propagating north of the Bering Strait, which is really uncharacteristic for most storms, because there's obviously limiting. It's difficult for the waves to propagate through the region, but nonetheless, we're seeing waves exceeding 4 meters on passing by the Chukchi coast, and several large waves exceeding 3 meters on the Beaufort shoreline. So it's an entirely different story with this future sea ice. We're looking now at the coastal response, and I'll get into how these different points are denoted here later on. But if we're looking at the coastal response out to the 10-meter isobath, we can see that the maximum significant wave height, and this is the median of the maximum significant wave height for each of these points. The historical simulation coastal wave heights are largely limited to less than half a meter for the entire Chukchi Coast, and for all of the Beaufort Coast, really. The small areas where it was exceeding that was shown to be an error in our actual simulation. So largely, again, we're seeing the protective effect of the sea ice during the storm. If we get into the moderate emission scenario, again, for climate model people, this is the SSP 24.5 emission scenario. You'll notice that the Chukchi Coast is now largely open. We're seeing wave heights within that coastal zone exceeding 1.5 meters, reaching up to 3 meters in some locations for regions that were really otherwise completely protected. So obviously this moderate emissions scenario is showing that this December storm could have significant impact on the Chukchi Coast, where previously it did not. We're looking at the high emissions scenario now. You'll notice that really, again, ever increasing wave heights on the Chukchi Coast, especially around the area around Nome, where we're seeing coastal wave heights exceeding 3 meters, where previously they were, for the moderate emission scenario, they were limited to 2 meters. And then for our high emissions scenario in 2070, which is really our worst case scenario, we're seeing that not only is the Chukchi Coast having a very high wave response, but as well as the Beaufort Sea, where maximum significant wave heights are exceeding 1.5 meters, reaching up to 2 meters in certain locations. Just to explain where these points are actually coming from, they're taken from the Arctic Coastal Dynamics database. So each of these is a named coastal segment with associated properties and its own shape. And I think I mentioned this, but we're going out to the 10-meter isobath to sample what we refer to as coast waves within the coastal zone. And you can see here that we have quite a few nodes in each of our simulation nodes within each of the locations. It can range up to 2,000 or more. And finally, our goal was to establish a relationship between the coastal response and the seasonal ice extent. And you can see here on the left, the Chukchi Coast, there's a clear upper boundary for this, what we refer to as the saturation limit for this storm. It's around 1.5 meters, averaging all of those coastal dynamics data points along the Chukchi Coast. You can see that the maximum saturation is typically for this storm historically denoted by the black line, with the shading denoting the upper and lower quartiles. You can see that maximum saturation extended till about October and reached till December, at which point the region is entirely protected. However, future scenarios show that by 2050, that maximum exposure could be extended by at least 1 month and up to 3 months by 2070. So this is obviously a large increase in the exposure towards the fall season. And here we see that for our worst case scenario, that's the high emission scenario in 2070, the region never really achieves full protection, even coming to the seasonal sea ice maximum in March, where there's still some degree of exposure. If we're looking at the Beaufort Coast, we get another surprising result in that the historical sea ice, both the lower quartile and the upper quartile, show that some protection is afforded by sea ice even during the minimum. So perennially, sea ice would have protected the Beaufort Coast from the largest wave heights that could occur during that. If we look to our future scenarios, however, all of them show that protection, that perennial protection occurring even during September, is gone, and the maximum saturation limit is reached and could extend by 1 month to October for most of the scenarios, and could even reach out to November for the worst case scenario. So that's the key conclusions that were derived from this study. And obviously, if we're looking towards the worst case scenario, that's that high emissions scenario 2070 to 2079, the dark red line. The contrast that we see between the high emissions and the moderate emissions really stresses the importance of curtailing carbon emissions, because if we're comparing the two, the difference between a single month of increased exposure and 3 months of increased exposure is significant. Finally, I think I'm starting to run out of time, but I'd be remiss if I didn't touch on some of our other research looking specific to the region. One is high resolution projections of Arctic waves specific to Alaska. Here you can see our model domain in the figure to the left. If it looks like it's a bit finer in that region, it's because it is, but the model domain reaches all the way over the pole and further south so that we can capture swells coming from either direction and impacting the coastline. And here we're deriving bulk wave statistics, the 50th percentile in mean significant wave height, or the 90th percentile, and projecting how those changed from the historical epoch, 1980 to 2020, and then looking at how they change into the future decades, 2040 to 2049. And here I should stress that we are using the previously mentioned high resolution climate models that have enhanced ability to simulate extratropical cyclones and Arctic cyclones, so both of those. Beyond that, I would also, oh goodness, there, let's go back. I should also mention that that we're looking at marine wave hazards, as I mentioned in the title, although this is a coastal presentation. And our objective here is to predict concurrent changes in Arctic sea ice and marine wave hazards along the Northwest Passage maritime route. Here we're predicting that the Arctic Northwest Passage could be viable for transit for an unclassified sea ice vessel for up to 5 months by the year 2070. And concurrent with this change in accessibility, there's a large increase in the regional wave climate. If we're looking at the 90th percentile wave heights and how they're growing, we see sharp seasonal contrast where early in the year, July, September, there's moderate increases, but November, with its increased wind climatology and more severe storms, we're seeing a massive increase of up to 50 centimeters per decade in the 90th percentile wave hazard. So this is a dimension that really hasn't been assessed in the current literature for analyzing Arctic maritime transit and some of the environmental risks that would be present there. So that's some of the other research that's going on and with our team, and we're hoping to make many of these outputs publicly available so that they can be downscaled to the coastal zone, especially the results coming from the latter study, and potentially feed local studies that are looking to analyze how their wave climate could change into the next 20 years up to 2050. So with that, I'll cede the floor, and I'm not sure, am I allowed to take questions now, or are we waiting till later?
I think we're going to take some questions for a few minutes. So,
okay.
Does anyone have any questions for Martin?
I think Maddie does.
I do. Yeah. Thank you. Yeah, it's a cool talk. Really nice work. Sorry if I missed this and you did touch on this, but yeah, I'm curious about landfast ice. I know that yeah, there's been a lot of work showing that landfast ice can really play an important role in changing the wave forcing right at the coastline compared to what we might see slightly offshore. And most of these models aren't able to resolve it for, yeah, largely due to the model resolution, but other issues related to representation of physics. Did you do any accounting for that in these projections, or what do you think is the potential role of that, how it might change over time?
So that's a really great question, and it's something that was accounted for in the design of the study, and I didn't touch on it in this application. I was remiss not to. So in the study that was recently published that I was talking about with that actually had coastal capability, we don't have the ability to simulate landfast sea ice. And as far as I'm aware, there's no existing projections of landfast sea ice, and that's obviously a limitation. Here, we really relied on the work of Lucia Hosakova and her projections or her assessment of sea ice and wave simulation capabilities on the Chukchi and Beaufort coast. And what we found in the seasonal cycle of landfast sea ice is that it's strongest. It's having its largest effect during the spring season. And so if you'll notice that in our seasonal exposure curves that I showed at the end of that at the end of that figure, they only extend out towards the fall, because really during that season, that's when sea ice or landfast sea ice is more fragmented and less capable of attenuating waves. And of course, there's been observations that under these weak landfast sea ice conditions, large storm fronts are actually capable of breaking up that landfast sea ice or pushing it onto land. But I mean, to bluntly answer your question, no, we didn't look at landfast sea ice. It's something that is really missing from the literature and that we would benefit from, but it's not accounted for. However, it wasn't accounted for by the fact that we didn't look at the spring season, because that's when landfast ice is having its largest effect and can persist for multiple months, where say some reanalysis products such as ERA5 or the satellite data products might be saying that there's open water and showing that the coast is exposed, but in reality, there's landfast sea ice.
Yeah, thanks for the answer.
Question?
That makes a lot of sense. Yeah, no, you did. Thanks very much. Yeah, and I'm definitely interested in this question of, I mean, I guess there's a question of whether the change in timing of that ice advance will be the same for landfast ice as it would be for other ice. Anyways, this is something I'm really interested in. So maybe we can talk more about it at a different time if you're interested. But
I would be interested.
Thank you very much.
That is one of the biggest remaining questions. And having any idea of whether that timing would change would be invaluable knowledge in informing future studies. Thank you.
Thank you for that question. We have a question in chat from Christina Bonzel. Does the limited extent of coastal water level observations limit predictability?
Whoa. This question does the limited extent of coastal water level yes, water level observations limit predictability. So the limited extent of those observations obviously imparts a large uncertainty into the regional simulation. However, it is here it's important to highlight that it is a regional simulation. We're not looking at a specific town or a coastline. So our hope is that to a certain extent that the error that is induced into our simulations due to the fact that we don't have the coastal water levels and how those affect wave attenuation or breaking or whatnot. We're hoping that, of course, that that error is averaged out over the entire region, essentially. I should mention that this wave model has been previously utilized and published and does show decent accuracy for the entire for the Pan-Alaskan region all the way to the South Central, and has been shown to reliably simulate coastal water levels all the way from, say, Prudhoe Bay all the way out to Nome or anywhere else. However, there is increasing water level observations obviously would improve the reliability of the model and allow us to tune it further. I'm not sure. Did I answer that question well?
Yeah, you did. You did.
Thank you.
So I don't see any other questions in chat. Does anyone have any questions for Martin before we move on? I just had one question. So Martin, you're gonna provide a publicly available wave climatology for Alaska. Will that
That's the goal.
include water level, storm surge calculation? Or is it just?
No, that will not.
Okay,
So the model that we're running for that one, for producing the wave projection for Alaska is WaveWatch 3, which can be coupled with ocean circulation models, but in this case is not. It's already extremely computationally expensive, and I won't be adding that element onto it. And again, it's actually not simulating the coastal zone for that wave projection. It has flexible mesh. It goes down to 1 kilometer. But really, with that resolution, we can't claim to be within the coastal region. However, it does have improved simulation of wave dynamics due to that flexibility.
great. Well, thank you. Well, let's turn to Lee, because it seems like we've gobbled up a lot of time. So sorry, Lee. But it was great to hear all that fresh off the press research. Thank you, Martin.
And I think you have to stop sharing, Martin, so that I can, there we go. Okay, let's see. Share screen 2. Okay. You can see a slide? Okay, great. And thank you, Martin. That's a great lead-in. Looking the larger scale, and I'm going to bring us into the more local scale. The title of this presentation is Coastal Flood Hazard Modeling and Assessment Tools for Alaskan Communities. I'm a research oceanographer at the USGS, Pacific Coastal and Marine Science Center, and we have a large team here that's working on the modeling and outreach and various other aspects on developing tools for Alaskan communities, coastal communities specifically, and other products. Some of the key team members for the modeling portion and the outreach are Anita Engelstad, Ann Gibbs, Alex Nairson, Rich Broussard, Maya Hayden, Dee Williams, Nate Wood that I've listed there. And also we work very closely with Deltares in developing and improving our models. And our main person there is Case Naderhoff. This work started, that I'll be talking about today, started with funding from the Alaska Climate Adaptation Science Center a year and a half ago. And then when Typhoon Merbok hit, we were able to obtain further funding from the Disaster Relief Supplemental that supports this modeling as well and expands it to a broader geographic area. A little bit on the needs and the relevance. I don't need to go into much of it because everybody here knows, and Martin also talked about this. Storminess is getting worse. For example, here we have a photo of Golovin in September 2022, so that's Typhoon Merbok. Golovin had before been inundated back in October 1913 when the berm was overtopped, and there was a storm event also in 74, but it was protected by sea ice at that time, so nothing bad happened really. But now in September, this is an example, you can see the extensive flooding, and it's not the only storm in recent history. In addition to increased storminess, in some regions along the coast, the relative sea level rise is rising. On the left-hand side is a figure for NOAA that was recently put together by the Interagency Sea Level Rise Task Force. And it shows the projected scenarios of intermediate low and the high scenarios for sea level rise that were published for NOAA. On the right-hand side is a paper that just came out last week by Rich Broussard, where he looks at the impacts on communities from sea level rise. So it's current and projected flood exposure for Alaskan coastal communities. And there he intersected the elevation or sea level rise for the 0.5 meter and the 1 meter. The 0.5 meter is on the top and the bottom is the 1 meter sea level rise scenario with structures in each of these census areas. And you can see the Bethel census area is most impacted, followed by Nome. And the issues that the communities are facing are pretty dire. As you know, some of them are needing to relocate completely, or at least consider it, and cannot just move. It's expensive. It takes decades to plan, get funding, and lots of red tape. And there are social and cultural dilemmas with relocation. Communities are making plans today that could decrease the risk for many decades as they're planning for the future and making relocation plans or rebuilding if infrastructure has been impacted. But to do that, they do need relevant and accurate information, flood hazard information. Additionally, overland flooding is predicted with very sophisticated tools with National Weather Service, but when it comes down to the local level and overland flow, there's not that much data available. So to that end, we're developing 2 actionable user-centered products for more than 20 communities along the west and north coasts of Alaska. The one I'll be talking most about today is the long-range planning product, which aims to map future coastal hazard maps with sea level rise and storms. The target users are planners at the local level, city tribes, and Native communities, state, federal levels. And that is intended for long-range planning, for example, to guide rebuilding options, support funding applications, and preparation of mitigation and hazard plans. The other thing or tool that we're developing, working on, is to assist National Weather Service and emergency manners in responding to pending storms. And this work builds upon what we're developing from the long-term simulation, the long-range planning simulations. I'm not really going to talk about that today, but if there's interest, I can elaborate on that. Who needs the flood risk tools for Western Alaska? As I've mentioned, it's needed on the local level for community leaders, also for regional supporting organizations. Some are listed there, and countrywide supporting organizations. And some are listed there as well, and researchers and modelers. The approach we're taking for this long-range tool that we're developing, scenario-based products, we mean for them to be timeless. And by that, we mean that we're combining various sea level rise scenarios with plausible future storm conditions at the local level. So we have 6 sea level rise state scenarios that you see there on the left side. And we're combining that with 5 future storms and the no storm. So that would just be the sea level rise. We're simulating that and producing these flood hazard maps that include the flood extent, the flood depth, hazard velocity, flow velocity categories, wave heights, storm event erosion. And the reason for doing this is we want it to be a flexible product. We know that sea level rise projections, they change all the time. They continue to be improved. So for example, if we look at the 0.5 meter sea level rise scenario, that can be for a planning horizon of 2055 if you're considering the high emission scenario, or the planning horizon out to 2100 if you're considering the low scenario. So by combining all the return probabilities, extreme storm events with all the different sea level rise scenarios, we can generate more of a timeless product that can be used as sea level rise projections go forward. Some of the products, so here's an example. I'm just going to show you 3 slides of the flood hazard. So this is the depths and the flood extents for Unaclete in this case. Here we have the 100-year projected storm. These are preliminary results, so not for citation or distribution. And you can see here, this is for the 0 sea level rise scenario, future 100-year future storm. And if we run the model again with a 50 centimeter sea level rise and the same storm, we could get it higher, and thus far and continues as one would expect. And on mapped also is a GIS layer of infrastructure of various kinds so that one can assess the exposure and the followed vulnerability. And how do we get those static maps? Those, while they are static, all of the simulations are dynamic. So we include the waves, the storm surge, tides at the local level. And these models are running at as fine as 10 and 5 meter resolution over land flows. So what you're seeing here is a oblique image of a small portion of the Unalakleet model, just to highlight that. Another way to look at it is drawing a cross section across this model here, model domain. You can see on the bottom the waves that are approaching and overtopping the fronting dune, and this is zoom in on the very, very bottom shown here. So how do we get there to that local level simulation? And we have, when we're forcing it with future conditions, we're basing this approach on the coastal storm modeling system, which is a modeling train that we've been developing for more than a decade. We started in California and have now applied it on the South Atlantic coast of the United States and are working in the Pacific Northwest as well as the Pacific Islands. And we've amended it here to be applicable and used in Alaska and focusing in on the communities to start with where their most need is. The check marks that you see here indicate that we've finished our global scale modeling and our regional scale modeling, and now are working on that local scale. At that local scale, what does that entail? That entails first developing high resolution topography digital elevation models, TBDEMs, using the latest and best data that we can find, and then go into the model development and production runs, post-process, do internal QA/QC and reviews. And HERA is the hazard exposure reporting tool. That's where the data will be displayed and intersected with GIS layers and of census and infrastructure and such. The bottom shows more or less a graphic of the train here for this local level steps simulations. The forcing that we use for these local level models are derived from, as I mentioned, from the global and regional scale models, similar to what Martin was talking about. We've been running CMIP6 high res, some of the same that he's also has been looking at, the high res models. And in this case, here we're combining 4 different GCMs for an ensemble. And as well, we're looking at the ERA 5 reanalysis and running the storm surges and waves for that. Alongside, parallel to this is we want to ensure delivery of useful and usable products. So there's a big component in this project is outreach and engagement with the objective of producing actionable user-centered products and to ensure that target end users are aware and have access and understanding and use of the products. And they're part of, the end users are also part of the development in the very beginning. So before the modeling begins or just at the initial start of it, we build relationships with community members and planners and such. We identify the end users and needs. And when we get the modeling going, for example, we try to connect and ask about feedback on the digital elevation models that we're developing, as well as the model extents, because sometimes we might miss an important area that we didn't realize was important. So we have extended models in response to that. So we're collaborating small groups of critical end users during the model, while we're doing the modeling. And when the products are to be released, which we expect the first 3 communities this fall. We'll start a training phase where we'll do more broad outreach and make sure that end users know how to access and use the products. And then throughout the life, the application of the products, we intend to provide technical assistance, on-call assistance, either by phone or email, which we continue to do for here. Some of the outreach that's been happening over the last year, 2023 and 2024, we had project introduction for Unaclete and Elam, visiting the communities. And in 2024, project follow-up for Unaclete and Elam and introductions for Golovin and Shaktoolik. We're growing a network to reach more communities. And for example, we had a booth and a session at the Alaska Forum on the Environment. And this is my last slide to wrap it up. If you're curious about this project and want more information, I've listed the 2 websites for the 2 projects up there and our emails for contacts. And that's it. That's all I have. Thank you.
Excellent. Thank you, Lee. Does anyone have any questions for Lee? I have one question, Lee, and that is, are you incorporating or are you thinking about incorporating ground subsidence due to permafrost thaw or other reasons in the long-term projections?
Yeah, so we're doing that at the back end, so to speak. So we're working with a team at Virginia Tech who are looking at SAR imagery and getting vertical land motion rates for the last 20 or so years. Now I know we all know that that's probably not a constant rate, but we're assuming that to be a constant rate. And our flood hazard models, we project those we have those on the land surface, and then we raise and lower the land surface accordingly. So, and that way we provide an uncertainty.
And I'm just kind of curious, what resolution is that subsidence data? Is it like a kilometer scale?
No, it's, I'd have to double check, but it's on the meter scale.
Oh, wow.
Yeah, I would say I can check. It'll give me a couple minutes, but maybe some meters, several meters of that order. Yeah.
Great. So, does anyone else have questions for Lee?
I have a question I can't figure out. I feel like Google changed, so Google Zoom. Anyway, Lee, this is really interesting work. One of the questions I had was for the future projections. You showed those 4 GCMs. How did you choose those? And is it like a range of different model uncertainties, or what was that criteria?
We were piggybacking, you could say, on work that was being done in the Netherlands by Sun and Mui, who started off a modeling effort with the global tide and surge model, which is now operational. But besides that, that work focused in on the high-res MIP models. So the highest resolution CMIP6 models that Martin was talking about can resolve finer winds and supposedly typhoons and such.
Awesome. Thank you.
Mm-hmm.
Any other questions?
I think Andy has a question.
Good to see you again, Lee.
You too.
Yeah, this question or questions kind of 2-parter, could be for both of you. So these high res MIP runs can have different change characteristics relative to kind of the core SSP models. Have you, either of you looked at that and tried to understand that for the Arctic? Because, you know, the high-res MIP is kind of a different thing than the core SSP runs as far as the model configurations and parameters haven't necessarily been tuned for those resolutions, et cetera, et cetera.
So we ran one SST model, and then the other three are forced by, not by the SSTs, but by the atmospheric forcings. I have not dug in. What we've done here on this end, we've started to look at the variability between the models themselves, but not compared to the baseline SSTs. We haven't. I don't know about Martin.
No, I haven't either. Most of what I'm currently doing is just relying on the existing literature, especially I think it was a study looking at storm surge on a global scale, and utilizing those high resolution models. But you've given me something to look at now.
Yeah, it's just, yeah, all of these models potentially have such different change signals across, you know, circulation, change, windiness, even sea ice for the high-res MIP models. I'd be curious to see how they even perform for basic metrics relative to the other models. And then the other thing is just, have you done any bias correction or anything for wind for, you know, even at a 1/4 degree relative to what you might see at sub 5 kilometer wind maxima and things, or does that not matter for these types of simulations?
I think it matters, but I think it matters less because we're at a higher resolution than compared to the native resolution GCMs. And I think that at the scale of the WaveWatch 3 model, for example, which is on the kilometer scale at best, ours goes down the way ours is, the WaveWatch 3 goes down to 7 kilometers along the coast, actually. So there, and we're keeping those runs with outputs at 20 meters for us. And I think that doing bias corrections on the winds would not affect it that much. Once we're getting, though, into the near shore and into the coastal zone, it would be very good to have bias corrections or further downscaling of those winds. So I believe we are definitely missing something there. Could be done with WRF or something of that nature, but at this present time, I only know of CMIP 5 WRF downscaled. I don't know the CMIP 6 high res at least.
Yeah, thanks, Steve. This is super cool stuff. Sparks the curiosity.
Yeah.
So any other questions? And that the final item up for today's meeting is team member updates, but we actually just came to the hour, so maybe we're gonna have to pass on the updates. Unless anyone wants to provide an update right now.
I just dropped a quick link in the chat for a form. IRPIC is in the middle of updating our implementation plan. This maps out for 2 years what IRPIC will be focusing on. So if you have opinions about what, or knowledge about what kinds of things IRPIC should be working on, please let us know through that form. And also thank you everyone for presenting and showing up today.
Yeah, I think it was a great meeting. Thanks for all your participation and certainly thank you very much to our excellent presenters. Wonderful job.
Yes, thanks all.
Thank you. Thank you very much.
Bye, y'all.